job doing that.
Right.
Well, nobody
Okay.
teaches it.
Flying to bed.
It's exactly right.
But it's a dead-end technology.
But it's not.
Eventually-
But it's not, and this is the key.
Mhm.
They estimate, in this article, estimates that over 95%, now think about this, 95% of every single card swiping point of sales transaction, not globally, think of that, 95% is processed by a COBOL line of code somewhere.
Mhm.
Now you tell me that's a dead technology. That's not. It's huge, and the people.
I think the clock is ticking. At some point, they're going to have to upgrade to something more efficient.
With all the hacks.
Yeah.
But COBOL runs the financial industry. That's the one industry COBOL was written for, and they base their livelihood on that. And right now, your COBOL programmers, your young COBOL programmers are my age.
Right.
Okay? And so there is a huge need in COBOL. And I told my 18-year-olds 2 months ago, I said, if you're looking during the summer because you're bored and you're flipping burgers at McDonald's and you want to learn a new language, go learn COBOL. Just to have it in your quiver is going to set you aside and it's going to get you a job in a heartbeat. So I'm just letting you know, I agree. I would not want to be a COBOL developer. However, I will gladly be a COBOL contractor for $100 to $200 an hour.
Mm-hmm.
That I'm okay with.
Fortran,
Right.
Yeah.
Right.
That was what I used to
Okay.
understand.
All right. Sorry, we're.
Yeah. All right. Well, thank you everyone for coming to the Tech Academy. My name is Mike Allen. I'm the outreach specialist. This is our third series with Brent Wilson, Dr. Brent Wilson from George West College, and he's going to speak more about basically things you need to know about just thinking about developing in a secure application. So with that, let's give him a warm welcome.
Thank you. So, yeah. So what I have, I made some. Let me pull some of these additional copies up. So I made additional copies, about 15 or so copies from last week, and about 15, 20 copies from the first time. So if you weren't here at any of those and just wanted to grab my notes, I wanted to make sure that they were here. This is the set. If you can binary distribute those, it'll go faster. Log base 2, as a matter of fact. So, can we kill these lights here, or is that a problem for the camera? Where did my helpers go?
Lunchtime.
Yeah, we got this guy in here. We're out of here. He'll keep them involved for an hour. Okay, we're just going to do it. Thank you. Somebody's just going for it. Oh, okay. All right. So I'm assuming we're streaming online because I see the big camera. Yeah, week 1 and week 2, I put them over there, so when you leave, you can grab them for sure. And there's a whole bunch more of these as well. So, in fact, I'll just put some over there. You want to just set them on that table? That way, if anybody comes in and needs those. So, if you're online, welcome. And what we are looking to do today is really this sort of the third week that we've done this. My goal in all 3 of these weeks was that by the end of today, if you've been to 1, 2, or all 3, I want you at least being able to walk away thinking about how do I consider security in my development. I'm assuming we're streaming, we're live, we're good. Okay, all right. And in fact, it was interesting not to point you out because you're not on camera, so you don't have to worry about that. But before this started, we were just chit-chatting here over lunch, and one of your fellow classmates just mentioned that after last week, where we talked about indirect object references and being able to, once you're authenticated into an app, to be able to move based on looking at a path in a URL, to move somewhere where you shouldn't have access and you actually gain that access. Was actually working on an app himself and went back and tested it, and sure enough, he has that exact vulnerability in there, and so was able to resolve it, right, by going through and authenticating. So at the end of the day, at least we have solved one vulnerability. So I'm excited about that. So in the first week, we looked at injection attacks, which is really the absolute foundation for pretty much all attacks. It's really, at the end of the day, there's some sort of an injection. That's really what happens. And so then in the second week, we looked at not only some injections, but also how do, by injecting other types of either malicious code or references to files or URLs, how can we get things executed as a user? How can I inject what would appear to be just a string of characters and have you actually execute it instead of do some validation? So, and there are these for the third week that are up there. Sorry, folks that are online. If I use the word this and these a lot, you have to guess. So, which all of that leads us to today. And today we're going to dive deeper. We're going to actually look at the memory structure of machines, how do programs' memory work, what are the different registers, how do pointers work. We're going to start diving into that. I worked out and went through this demo, and I realized when I was done this last week, had I come to today and actually just did the demo, it's very difficult to see. And I thought what would be better is to literally, more or less, teach the vulnerability versus just demo it, okay? So today we're going to do that, because I don't know your backgrounds as far as, I could probably guess on this. How many people have ever had an architecture class? Wow, that's about
Software
4.
architecture or
No.
physical architecture?
Physical architecture. All right, so that's about 3 more hands than I expected to go up, which was a total of 3 for those that are online. So what we want to do is we want to dive in and sort of give you that background of what is this, how does it work, and we'll actually, I want this to be interactive, so I'm hoping everybody has one of these, and I'll just be answering questions and things as we go. For those that are online, when I say I have one of these, I'm talking about the Word doc that I have open. We're pretty much, this is what we're going to be looking at throughout, and we're just going to sort of walk through this. So let's talk about from a very high level. You know, our goal today is looking at a buffer overflow. What is it? And not only what is it, we're going to actually, quote unquote, do one, meaning that I've done it and given you screenshots, and we'll look at it that way. At the end of the day, what a buffer overflow means is that there's a set of memory that you have that's designed to hold X number of characters, and you try to put X plus N characters into it. I mean, that's really what a buffer overflow means. And so a nice way to think about this also, for those who've never heard of this or seen this before, think about, for a moment, let's say you had a table on a Word doc, okay? Let's say it's an invoice. It has 2 columns. First column is a description of whatever you're invoicing, and the second column, I should go this way, I should go my right to left, which would be your left to right. So the first column is a description, followed by just the price, okay? Well, if I started, if I type in a small description, and then I go over and type in the price, it looks normal. But what if I typed a really, really, really long description, and at the very end I put some numeric values in it? Assuming you could overwrite columns, I could push that all the way over to where the description actually is sitting in the cost call it. Does that make sense? So I could overflow that description, and it would look as though the cost is no longer $100, but it's $10,000, even though I never changed the price. That's sort of this idea of a buffer override. We want to do that in memory inside the computer. All right. So for today's conversation, we're going to assume 32-bit system. All right. I know we're all on 64s. Let's just make it easy on ourselves for today. Okay. So 32-bit system means that all of the registers inside your CPU are 32-bit. So you got 4-byte registers. They hold 4 bytes apiece. And when you look at any program that runs, all right, when you run a program, so we'll look at this, the picture. Basically what happens is the memory in your computer, high addresses will put up top, low addresses, so memory is sequential. And so your addressing moves from low on upward. At the towards the bottom in the low address is where the program text goes in. That's the actual source code, if you want to think of it that way. All right. So that can go into there. You have, if there's any type of initialized data, that goes on top of it. We won't worry about the uninitialized. Then you have in the middle, well, actually, ignore the middle. Go to the very top. If you have command line arguments that are being sent in, environmental variables, things like that, that all goes at the top. And then you have this big block of memory in the middle. And you have what's called a stack and a heap. Okay, you might have heard those. I'm sure you've heard the word stack. You may not have heard the word heap. So stack and heap are basically dynamic memory that you're able to allocate and deallocate. And what goes into each? Well, into the stack is all of the local variables for whatever function you're in. So you could think of whatever type of, if you're calling a particular function foo, and we're sending in a couple variables as parameters, those are going to end up on the stack. If foo has local variables, those will end up on the stack. If the program as a whole has either global variables or some sort of static variables, those go on the heap. And so these two areas sort of grow together, all right? And so that's sort of the big picture, if you will, of how memory looks inside the computer when a program runs. Now, inside your CPU, you have a number of different registers. Registers is literally, think of it as a, easiest way is think of it as a memory address, but it's internal in the CPU, and it's going to keep track of various things. There's a number of different registers. There's only 3 that I want us to understand. The first is called EIP, and E stands for extended. That's when we went from 16-bit to 32-bit. We added the E. I know we're past that now. But anyway, it's an instruction pointer. That particular register holds what is the address of the next executed line. Okay? And so as a program runs, every time it executes a line, that EIP gets incremented, and not always by a count of 1, because instructions could be short or they could be long. But anyway, that EIP gets incremented, so every time the CPU is going to execute, it looks at the EIP, and that's where it goes to execute. All right, does that make sense? It's just a pointer. Execute this line, then this line, then this line, then this line. Okay. And as you call functions, right, then all of a sudden it comes over here, execute, come back, go over here, execute, come back, right? It's sort of the flow of control. Then you have what's called a stack pointer register and a base pointer. A stack pointer stores the address of the top of the stack. The stack grows down, all right? The top of the stack in this picture is the bottom, okay? Because as you push things on the stack, you're moving down, your addresses are actually reducing. So an empty stack, the address is higher than a full stack. That address is lower because the addresses are moving down. So stack pointer is basically where's the In this picture, we call it the bottom of the stack, although we think of it as top.
You're still
'cause-
accessing it FIFO though?
Yes, yes. First in, first out. Right. And then you have what's called a base.
Or LIFO,
It's
sorry.
last
Last in, first out. Right. So your base pointer register then is for every function call, there's essentially a frame of memory that gets added to the stack. And that frame includes all your parameters, all your local variables, things that are, think of that as things that are active during that function, right? Scope, right? Everybody understands scope variables essentially, right? During that scope. And a base pointer keeps track of where that starts in the stack. And so you'll notice in a moment that a base pointer points that all the local variables are below it, all the parameters coming in are above it. So it uses a base pointer, the computer uses the base pointer to, if you want to access a local variable, you take your base pointer and you subtract from it. If you want to access a parameter, take your base pointer and you add to it, right? You'll see that in a moment. A lot of cryptic stuff. I realize if you've never had an architecture, that's like, okay, I have no idea how this applies to anything, but hopefully you will. Right? We're going to take some baby steps and move through this.
So wait, where does the instruction pointer is to be pointing to somewhere inside the stack? Or inside
No.
the program text?
Yeah, it's down here. So
Right.
the instruction pointer is keeping track of where you're going. This here is essentially, think of this as the data memory as this program runs. All the memory that you're using is up here, but the program itself is outside of that purview. Okay, great question. Any other questions? Please ask as we go.
So the stack pointer and the base pointer would be in that memory area, basically.
Absolutely. In this picture right now, we would have, if this had, we were just in main, there were no other functions whatsoever, the stack pointer literally would be right here, and the base pointer would be somewhere in here. And I'll show you how we determine that in a moment. All right, so, oops, come back. So let's look at a really simple little function in this picture. So here is a function called f that accepts two parameters, two integers, and internally it creates two local variables. What you have on the right is a picture of memory as we execute this function. So the first thing that happens is that the value of B is going to get pushed onto the stack. In other words, somewhere there's a call to F, right? So somewhere you're going to call that function. The parameters need to be pushed onto the stack. They're going to be pushed in a reverse order as they're listed. So B is actually the first one pushed on the stack, followed by A. So B gets pushed on the stack, A gets pushed on the stack. The return address gets pushed on the stack. Where is that? Where's this going back to?
The next instruction after the call.
After the call. That's exactly right. Wherever this got called, this address is essentially that next instruction after the call. Everybody follow that? Okay. Then you also push on the stack the previous frame pointer, meaning that you were already in a function. And if it was main, it's main. If it's another function. But somewhere, whatever function you had a base pointer. When you're coming into this function, you now have a new base pointer because you have a new frame here that you're working with. Well, you have to keep track of what was the previous, because when we return to this address, what else do we want to do? You want to return that base pointer so you go back to the same environment, right? In other words, let's say you're in the function main and x has the value 99. When you go into the function foo and you change, assuming it's a value, or let's not even say it's a parameter, you go in, okay, I did x, no I didn't, okay good. So x now has a value 5. When you come out of that function, assuming it's not a pass by reference, and we didn't pass it in, when you get back out into main, what's the value of x? 99. How do we know that? Because this frame pointer is back to where the memory we're referencing is for main. Okay? Then, after that gets pushed on the stack, then we now actually go into the function. So all of this takes place before we even get really into this function at all. Once we go in the function, we now push on, we see we have local variables x, we push that on, and we push on the value of y. So the arguments come in, that's the number one thing. The return address comes in. The previous frame pointer, that gets pushed on the stack. And then finally, the local variables. The base pointer, yeah.
Do the local variables go in order versus reverse order, like the parameters did, or the arguments did?
Yeah, they go in order here.
Okay.
Yes. The parameters are always in reverse order.
Okay.
All right, so now we have these variables. The base pointer for the function f is right here. It's after you've gotten everything to come in, but before you start doing the local variables. Remember I said when you have a base pointer, adding to it, which goes which direction? When you add to this address, you go up or down? You go up, right? High addresses are up top, low addresses below. So when you add to it, you are able to get up and get the parameters. Now obviously you automatically have to add 8 bytes. You have to add 8 bytes just to get to the first parameter, because you've got to get past these 2 pieces of memory to reference what's up in here. And then to get to the local, you subtract. You move down. Okay. Where's the stack pointer in this picture? It's not here on purpose. You tell me where it is right now in the state of this. Where would the stack pointer be?
The bottom of the local variables.
The very bottom of variable y. This is where it's pointing. Okay? Because the stack, you're pushing values on the stack. That stack pointer keeps moving down with you. This is where the stack pointer is. Okay? And actually the second question we already just talked about. How is it built? On the call, at the moment you make the call from another function, that's where push a parameter, push a return address, push the frame pointer. Now you go into the function and push local variables. Okay? So that's what happens in memory. This is a lot of foundation in order to even get to buffer overflow. But we have to do it.
Quick point of clarification.
Oh, please.
On the return address, why is the return address the position of the instruction immediately following the calling function and not the calling function itself?
Okay, say that one more time. Sorry.
Okay, your third block down,
Right?
the return address, why is that address the address of the instruction immediately following the calling function and not the calling function itself? Why is that return address one step ahead beyond the calling function rather than?
Same spot you call the function again. You go back and do what you just did.
Right,
again.
so-
Oh, okay, that's interesting.
Mhm.
Yeah, yeah.
Thank you. Sorry. I wasn't. My memory was not working well.
Essentially, before
Right.
or after.
Right.
Right on, yeah.
When you finish, you head back to the next. Okay. All right. So a very simple function. How that works out. Oh my gosh, I just saw myself on TV. Can we get that magic eye to be up further? That was really scary. All right. Sorry, folks online. I like my pizza. Okay, so now, let me get, I'm not sure why I have all that on there. Let me take that. So now let's look at the exact same function that we just looked at. Well, not the exact same. Very, very, very similar. But I want to give it in context, which goes to your question. All right. So now we come in. We have a main function that calls the function f and sends in the value 1 and 2. And then, obviously, when it's done, it just prints out hello world. Okay. The function f, when you go in, it accepts 2 integers as parameters, comes in, creates a third local, sets it to 99, and you're out. Easy peasy, lemon squeezy, right? Okay. All right, so now if we look at the memory part of this, got to get out of the view of that one. All right, so now you see a much bigger picture. Here is when if we were just had a main function and we didn't have the function f, all of that memory would be up here. This is where you'd have a base pointer up here, you'd have the stack pointer up here, you'd have local variables, all your parameters, you would have the frame for the main function. What we want to do is look at what does the frame look like for that other function. And I'm just looking, so that camera is solely on this. That's fine. So folks online, I hope you can see it. I'm not sure. All right, so anyway, once again, we come in, we go to f, which means we push the value of 2 and then of 1 because they go in reverse order. So we push B onto the stack, then A. The return address, which is going to point to the printf statement, right? Because that's where we got to come back to when we're done. And then the previous frame pointer. The previous frame pointer is going to be somewhere up here, because it would be wherever the frame pointer is for the function main, right? Just based on what its variables are and things like that. Then we have a single local value x. So, again, where's the stack pointer? You guys are going to get good at this.
The bottom.
Very bottom. Where's the base pointer?
No previous frame pointer.
That's exactly right. It's below previous frame pointer. This is your base pointer. Everything above is your parameters. Everything below is your local variables. Everybody following this okay? Okay. Can you tell me what is the instruction pointer? What's in EIP, and not an exact address because I'm not giving you memory up here, just prior to setting x to 99. So this picture right now would be exactly correct. This has a value of 2, this has a value of 1. Depending on the language, this could have a value of whatever is in memory if you're using C or C++. Right? If you're using something like Java, this would have a value of 0. But just prior to executing this line of code, what's in EIP? What is EIP? It's instruction pointer. So if we're just prior to executing the line x equals 99, what's the instruction pointer? Instruction pointer.
It's going to point to x equals 99,
Point,
wherever
good.
that is in your program.
Exactly. It seems trivial, I realize. But I'm trying to get some foundation in because in a moment we're going to look at a lot of hex and memory. All right, so I want to make sure everybody's understanding how this all plays out. All right?
You're saying before it's executing the f function?
No, before it executes, before it sets x to 99. So in other words, when you look at this memory, because the value of x is on the stack, that means we must have executed the memory allocation. All right, and so now just prior to that. All right, how's everybody doing? Architecture 101. For some of us, it's review. For others, you're like, I didn't buy into this today, but I came for the pizza. For those online, you get the tech and no pizza. All right. So now let's look at a function that has a buffer overflow. All of that just to get here. Here is a simple little function, BOF, buffer overflow. It accepts a character pointer, so a string pointer. Inside, it has a 24-byte string character array called buffer to drive the point home. And we're going to use a function called string copy, which takes whatever's coming in into the string and copies it into our buffer. And then when we're done, we'll return 1. Where's the buffer overflow? What line up here might cause the buffer overflow? The string copy. Exactly right. Because there's nothing wrong with sending a string into the function. No big deal there. No big deal creating an array of 24 characters. But now blindly copy what you've sent in into a buffer of 24 bytes. You might have an overflow if what you're sending in is greater than 24 bytes. What does that do for us or against us? Here's the memory again. So we come in, there's your main stack frame. You have your stack pointer, that's the parameter that gets pushed. Return address gets pushed on. The previous frame pointer gets pushed on. Then the local variable, you got 24 bytes. And so you're going to basically push 24 bytes onto the stack. And then at this point, real quickly, make sure everybody's got this. Your stack pointer is where? Bottom. Your base pointer is where? Previous frame pointer. Good. How big is the previous frame pointer? How many bytes is that? We're in a 32-bit system. Remember that early? How many bytes is the return address? 4. What if I push, I don't know, 28? Maybe 32 bytes? What if I push 32 bytes into the buffer? What am I going to overwrite? I'm going to overwrite the previous frame pointer, and I'm going to overwrite the return address. So if I'm able to somehow inject malicious code somewhere, and then have this now go and return to my code, instead of where it was expected to go, now we got an issue.
So you're going to overflow the whole thing and then make it so it goes to your pathway instead of the original return.
Absolutely. The whole point on this, I am literally, the last half hour is all comes down to, I want this. I want to own these 4 bytes. Right? I want this going somewhere else. Okay? So what I do is by the buffer, the string copy is a known buffer overflow vulnerable function. All right? Don't use it in C or C++, along with a number of others. Which again goes to, how do you minimize vulnerabilities? Know what commands in the language you're using have buffer overflow or other security vulnerabilities, and don't use them. Right? It's blindly coding something, looking and say, oh, you know what? I got that in, I got to put it, I'm just going to string copy that, and away you go. You're thinking use case, not misuse case. Right? So understanding. All right, so we want to do that. So now, let's actually do this. So, from here, let's go to this little piece of code. Let's assume that the following source code has been given to us as an executable. Now, we just happen to, we're looking at the source so you understand for today's talk. But let's assume this is a binary. We don't actually have the source. Okay, we have the executable. That's all we have. And it just so happens this is the source, so you can understand. But what is the use case? What is this code supposed to do? If you were to run this, now you have to manually trace it real quick. Obviously, we start where? Main, right? So the first thing we do is we call echo. We go to the function echo, sets up a buffer, 28 bytes, prints, enters some text. We now, on the command line, we go ahead, we enter our text, type. Scanf is going to take what, is going to go ahead and grab that from the system in, and we'll place it into our buffer. And then it's going to print out, you entered, whatever. So if I ran this, and then this is done, when echo's done, where does it go? Goes down to the return 0, and then out. So if I ran this, on the screen I'd see, enter some text, Brent Wilson. You entered Brent Wilson. Done. Right? Secret function never gets executed, does it, in this code? Can we make it get executed? Yeah, we can. We can play with memory, and we can actually make this function get executed. So in this example, instead of us injecting some sort of a malicious script, we'll assume this secret function is a malicious thing, and we want this program to actually execute this code. Well, from a high level, how do we do that? What do we have to do?
Change the pointer to,
From where to where? Where do you want to go? How do you want to change the flow of control here?
you want to change it from executing echo to executing
I think you're gonna.
or the return, yeah, the return address.
Okay, good. So if we went from here, main, and instead of calling echo, we just went and called this, there's no buffer overflow there that I can exploit. I have to be able to exploit this. And given what I just gave you a moment ago, if I put more than 28 characters in here, I should be able to overwrite the frame pointer, and I should be able to overwrite the return address. And if I can overwrite the return address, then when it comes out of echo, I can get it to go up here to secret function. That's the goal. Is it doable? Absolutely. All right, so let's take a look at it. How's your hex? How's your assembly code? It's been a while for some,
Yeah.
including myself. But I'll tell you, lately I've been in it a whole lot more than any person should have to. I look at assembly code like having kids in college. It's sort of a necessary evil sometimes. All right, so what you're seeing, and again, for those online, that is a big black square. So, I'm sorry. So what we have here is taking this program that we just looked at, and it's an executable, so it's a binary, and now running it through something like the GNU debugger or a variety of other things that you can disassemble code. You can take an executable and have it disassembled into assembly language so you can see it. Not back into nice, beautiful, readable C or C++, but you can get it into machine code and look at it, right? So this is what we have. So when you look at this, you can see at the very top, there's secret function. There it all is. Underneath that is echo. There it all is. And underneath that is main. The very, very first column is a memory address. All right. So, so my first question is, what address does secret function Where is it located? Well, looks like 0804849D. That is the starting memory function for the secret function. That's going to be important to us because we're going to want to use that address as our injection, right? In other words, when we fill the buffer and we start overwriting memory, we want that to be the last thing that gets written so that it overwrites everything into the return pointer. Is this making sense? Told you we get a little deep today. Last week I'm like, we're going to dive a little deep for some. For others, you're just like, cool, I love this. So, the next question is, how much memory has been reserved for the local variables in Echo? Now, to help you out so you don't have to try to decipher that huge giant block, it actually is done in that one line. In this one line of code, it actually sets up a block of memory for all of the local variables, or for local variables that you might have. Now, everything I've given you up to this point showed things nice and clean, and I put in 2 integers and it only allocated enough for 2 integers, right? All my pictures were like utopia, everything works beautifully, right? This is a little bit more real world now. It isn't necessarily the case where, okay, we have a 28 byte buffer that we want. We're not just going to execute 28 bytes. It's going to actually reserve a larger amount of memory. Okay, so look at this line. I'm going to teach you a little assembly while we're at it. So here's what you're looking at. The memory address as to where this instruction is. The actual hexadecimal values of the instruction. So this would be essentially, well, it is the hex for it. Then this part here, this shouldn't maybe have this big space. That might be confusing. The instruction itself is this piece. Starts at sub, which means subtract. That's what we're doing. We're going to do a subtraction. And these are your 2 operators. What's an ESP? It's a stack pointer. And if you subtract from a stack pointer, where does that go? Down. So that means this one line of code is actually moving the stack pointer way down, which is allocating or reserving memory for the stack. How much memory are we reserving? Hexadecimal 3856. 56 bytes is what it's doing. And it isn't 56 ironically because I'm doing 28. That isn't the case. I realized that when I ran, I'm like, oh, I want to make sure to mention, it's not just double. That's not. It's just that's what this does. Don't ask me why. I didn't design the CPU at which this was run on. Okay, there's some trade secrets in there somewhere. So what this does is it allocates. So now you can think about the pictures that we've been looking at, and you know that you have a stack pointer that is 56 bytes down. That's my stack at this point. What is the address? We'll go to the next one. What is the address that EIP, or what is the address in EIP when Echo completes the line below? So this is the last line of Echo which returns. This line of code, now the program will look at what is in EIP, which is what's the next line to be executed. Where is that going right now? Anybody know? You can tell me generically, or you might be able to tell me more than that. Where's the source again? Can anybody give me an exact? It's a little tricky, isn't it? Because you got to decipher this. Well, in general, where is it going to go? When you return from echo, where do you go? You go back to main, and you go to the next line after the call, right? So when you look at that, that would be at 8048502. Does everybody see that? And that line of code, what does that line of code do? Does it actually return? No. That line of code moves 0, the value 0, into a register called EAX, which we won't go over. And then the next 2 lines is when it returns. So when you return 0 as a line of code, when you write return 0, that's actually multiple lines of assembly code. The first thing you have to do is you have to load the registers with what's the value you want to return. And now we actually return. It actually has to be done in multiple steps. Okay. Why did I ask you on this one where this goes? Because I don't want it going there. Right? I want it going somewhere else. I want this instead to go to 0804849D. Right? I want it to go to secret function instead. Right? Okay. How's everybody doing? I figured this was a lot better actually on paper than to try to sit here and run it, because you couldn't see it, and this way you can write some notes. So hopefully it's helping a little bit to do it this way. All right. So now what's the size of the buffer? Now when I say buffer, I mean truly the local variable buffer. Okay? What's the size of that? This is the line of code where it sets that. By the way, EAX, I might as well cover it because you've seen it a number of times. There's multiple registers, like I made mention, and I only shared a few of them with you. There's one that's called the Accumulator Register, and that's where anytime you're doing arithmetic, you're always loading that to, that's sort of like your base, your primary little memory location that you use for operations. That happens to be called EAX. So in this case, what we're doing, we're going to load an effective address, LEA. We're going to load the address of whatever this is into that accumulator. Well, I'll give you a hint. This basically says subtract that from the base pointer. Well, if we subtract from a base pointer, where do we go in memory? Down. We go down into the stack, don't we? Okay, I'm going to scroll up for just a moment and make sure we're all having frame of references here. Given a base pointer, if we subtract from that, we move down and we're getting into our local memory. When we add to it, we go up and we get into parameters. So in this case, we're going to subtract hexadecimal 1C from the base pointer. What's 1C in decimal? 28. Nice. Your conversions are good. All right? And why 28? What was
It goes reallocated.
That's what we wanted to allocate, isn't it? So all of a sudden what we've done is this line of code says, give me the address from our base pointer, go down 28 bytes, wherever you're at, that in the stack, that's the piece of memory I want to start using. That piece of memory is the beginning of the buffer. And when I say the buffer, I meant the local variable. Shouldn't have named it buffer, huh? Too many definitions there. So this one line of code does that. So now, here's the question. After all of that, we have sitting in this EAX, we have sitting in a register, we have the value, or the address, I should say, of where our local variable buffer exists. How much data must we push into that buffer to fill the buffer, overwrite the base pointer, and overwrite the return address?
36 bucks.
You're off by 4. 32. Because we're four bytes per, right? So you got 28. 28. For those that are not online, I'm doing this. I'm going 28. I'm showing them 4 fingers. I have no idea why. I have to do some quick base conversion and come up with some value that's 28. So you have 28 plus now 4 for the base pointer register plus 4 bytes for the return. We need to push 32 bytes of information into that buffer. So when it asks us to enter some text, we want to enter 32 bytes of information. The key is the last 4 need to be what?
Address or secret.
It's the address. It's the address of the secret function. Right. Okay. So now that you know that, at the very bottom of this page, I put some additional topics that you have to understand in order to finish this hack. And that's something called Little Indian, Big Indian. Yes?
Quick question. So why wouldn't it be 36 though? Because you have your buffer that's 28, right?
Yeah.
Then you need to do the previous frame pointer and the return address.
Oh, did I miscount?
4 bytes each. So
Oh,
that's
I did miscount.
It's 36 if you include the address of the.
Yes.
Right.
Yes, it's 36 if you include the address. 32 pieces of garbage
To get there.
to get there.
Or-
Thank you. You're right. My bad. My bad. My solution's correct. The way I said it was not. Yeah. Okay, very good. Absolutely correct. So 28 plus 4 plus then the addresses. Excellent. Okay. So Little Indian, Big Indian. Anybody knows what those are? Care to share? Or not? You're like, I know it, but
It's how numbers are stored, whether you store most significant byte first or least significant byte
yeah.
first.
When you store, let's say you store a 2-byte number, do you store the high byte first or the high byte second? Right? How is it stored in memory? And your architecture will dictate that, depending on what it is. So in this case, we're using Little Indian, which means we have to reverse everything. Okay? So if our return address in this case, which I don't even remember, I printed front and back, I forgot. So the address we want to put in is 0804849D. We have to actually reverse all of those bytes. And when we write it into memory in order to get it in the correct order, given this architecture, you have to write 9D, then 84, then 04, then 08. All right? Everybody follow?
How do you know that you need to do it in memory? You just have to know.
You have to know. Or you got Google's your friend.
Okay.
Right? What are you working on? What type of architecture are you working on? Okay. So, so the other piece that you have to know is how, because remember, when this runs, you're at a console, you have a keyboard. What do you have the ability to type? ASCII. What's the ASCII for 08? Oh, there isn't anything, right? You have to, somehow I have to get these hex values in by typing ASCII on the keyboard. And you can do that. And the way you do that is the last item, and that is how do you print hex values? You actually type the /x and then NN, and those are the 2 values. So if I did /x08, it will actually send in the hex value 08 as input. Okay? The third, well, I guess the second bullet, because I skipped. Every week I've skipped something. The second bullet is piping. Do you guys understand piping at all? How you take the output of one process as input to the other? You've heard of it? Okay, if not, let's assume not. Basically, operating systems allow you to, you're running different processes, and I can move the results of one command. Instead of printing them out, I could actually pipe them, push them into another type of command. All right? And so here, what you could do is, if we and again, I'm not going to run this, because every time I run it, I got a little bit different addresses, and I thought that was the other thing. I'm like, the second I print this and then go up there and run it, all my numbers are going to be totally different, because it's going to put it in a different spot in memory, which is why we stayed with paper today. But let me show you, and I will type. So what I could do in this case is, to get this to run, I could use, if this is an executable, normally I will call it, I don't even know, call it foo. If I'm on a command line, and I do most of my stuff in Linux, so that's sort of where I'm going here, and I know you guys are more Windows-based. But you can still, obviously, you do command line within Windows, it's not a problem. But I can execute by doing like /foo, and it will, for those that are online, hang tight. Come on, where's my, you get so used to the ribbon. There we go. So this would just execute it, and that would come up and it would say, enter some text, and I would type Brent Wilson. It would say, you've entered Brent Wilson. Okay. What I want to do is, I don't want to enter from standard in. I don't want to do that. I want to take the result of something and push it into this program. And so when it's looking for standard in, it will take the results of this other process. Python is awesome. Python is your friend when learning to hack. So I can do this. I could run a Python program real quick, where I could literally create a program that just did something like this. If I did print, okay, thanks Microsoft. All right, tell me what this does. You Python people. Forget the .foo for a moment. Anybody remember what that does in Python? Anybody know? What's that? 32 A's. It's a lot better than going 1, 2, 3, 4, 5. Just a second. Now I got to back up and remember where I was, right? Right. So that'll print 32 A's. And then I also want to print, I want to take that string plus now the string, and I can now go /x, I forgot what I've got in here. I'll do /x9d /x 8/4. You guys are not helping me out.
8404.
Thank you. See, if I don't have to look down at the paper, it's a lot easier. 08. Okay, so I take that, and in Python, if that's my program, what I can do is I can actually, let's see here, I could run it as its own, let's say it's in its own file. I put that into some file called hack, okay? So that's inside of hack.py, okay? So then down here, when I go to run, I can literally just do a Python, if I'm doing 3 for me, it's Python 3. Python 3 hack.py, that will execute it. Pipe, which is the bar, it's a shift right above the return key. It's above the backslash, there's a pipe, right? Or, right? You guys do or with double pipes, so you guys already know. I always have to explain a pipe to people, and I realize, not you guys, you're good. And so then if I just do that, Python 3, which is now going to execute this file, but instead of printing to standard out, instead of printing to the screen, it's going to take whatever that program produces and it's going to push it into that program. So when this program runs, it will get 32 A's followed by these bytes. And now when I ran this program, what would it do? If I ran that, it should say, I gotta get to my thumb. It should come up and say, enter some text. You should see 32 A's. That's all you're gonna see. The others are not printable. Because it'll say, enter some text, and it says, you've entered, and then it'll show A. Congratulations, you've entered the secret function. Because what we did is we replaced the return address with where we wanted it to go, not what the program wanted it to go. That's a buffer overflow. And I thought that having this would be nice for those who haven't seen this before, rather than sitting here trying to actually run it, because the screen's tough. So for those that are online, make sure you touch base with the folks here. They have extras. And the other thing, I'll get you the digital copies of all this, so then you can post those if you wish. All right. Questions or comments on this? Yes, sir.
How do you get into this? How do you get this? What percentage of attacks are using this methodology?
If I were to do, let's say if I were doing this and I didn't have the source code, all I had was I could run it and it said enter some text, enter my name, and it told me my name. It might be secure because it may not use one of the functions that have a vulnerability in it. Okay? If it does, I'm not going to just magically poof be able to get it. What I would do is I would actually build a brute force. So I'm going to build sort of an infinite loop thing. And I'm going to start pushing this thing like crazy. That thing may run for 60 hours. And if I can break it, then I'll know exactly where I broke it. And I've, in a controlled environment, have done that before.
So when you do that and you're trying to brute force, you're just trying to find where you can finally sneak into that buffer overflow.
Yeah, there's some things that I would do first. First thing I would do is I would throw at this probably a lot of %S's, right? Because it's going to try to print strings. If this is printing, it's going to think there's other data out there. So I might throw a whole string of %S's at it. It's going to do a core dump. It's going to segment overflow, and you might be able to get some information from that. And then I can use that and start coming back and narrowing it. The things I showed you, right? There's some black magic here, and it's not like you just sit down and magically are able to get into these things, right? I mean, I've walked in with just the perfect environment, and you know what I mean. I've walked in, and in this exact situation, here's how it would work. But for those in the room who've never seen a buffer overflow, that's exactly what you needed, so that you could actually see what happens. Now, when you really get into, well, I actually want to do the attack. Not sure I want you to do that, right? So, but yeah, what you would end up doing is you'd do some brute forces and see whether or not, how is that being used. The other thing is breaking, well, you know what? Go to the assembly, right? Look at the call in the middle of echo. On the 84DD line. It's calling scanf. I got it. The scanf is vulnerable. That's one of the vulnerable functions. And so just by disassembling it, I know I have a buffer overflow vulnerability in it. Just because of that additional information on that line. So what are key functions in C or C++? Get S, scan F. What are the others? Oh my gosh, there's 4. I can't remember that too. String copy, yes, we did that one. And there's one other too, and I forget what it is. But they're known, right? Google's your friend. Doesn't take but a minute to realize.
How do you know that it's called scanner?
Oh, look on the right. See where it says call. It's got some addresses. Inside the less than greater than, you see a scanf at. Yeah, as soon as I see that scanf, I know that you're using that. Now it doesn't show me the line of code, but I now know you're using a vulnerable piece. And I could have easily found that literally within 15 seconds or less, because all I had to do is disassemble it, scan the code. I see scanf, that's got a vulnerability. Now the next 2 days is going to be trying to break it.
That's if you have the executable in previous systems.
Right, exactly. Yeah, this is, the first couple times we met, we just talked a lot of web stuff. I wanted to show you, sitting here on a machine with an actual exe or whatever, right? Well, I hope over the last 3 weeks you learned a little bit. If nothing else, you are able to check some of the stuff you're doing and minimize those vulnerabilities. That's the whole point. And even if you can't do any of those, whatever company or corporation you find yourself in the next months that you're on a team and you're talking about a project and they're going down a road, just to ask the question, are there any security concerns we need to know about in doing this, or we need to think about? Because you may not know the answer, but they do, but they're not thinking about it. And that right there will save the company that you're working for tens, if not hundreds of thousands of dollars in the end. And that's important. So, well, thanks for the time, and I appreciate letting me come in 3 weeks in a row. Although I don't like Portland traffic.
So thank you for coming. If you could, take a moment to fill out a survey of your experience. Any feedback is greatly appreciated. It's helpful for us. And just take a moment to fill it out. Thank you. Any questions? Feel free to talk to us about the school.
If they never ask me back, I know what you filled out.
Thank you very much. Appreciate it.
This is in white. It's been 10 years since I've been baseball football.
Sure. Well, and
We
it's,
had a Dick 10 system.
oh yeah. And you get pretty low level, and again, there's a lot of folks who have never even